Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to give you a tutorial solution on question 6 of tutorial 2. For question 6, a seaside resort plans to build a jetty to attract more tourists. The jetty will be constructed using reinforced concrete where the plan view and cross-section view are shown in the figure below. It is estimated that the characteristic variable action on the jetty is 4 kN per square meter and the finishing is 1 kN per square meter. The jetty is on the coast and must be designed for 1 hour fire resistance. The following information are also available. So concrete characteristic strength FCK is 35 megapascal. Reinforcement characteristic strength is 500 megapascal. Main reinforcement diameter, we are going to use 25 mm, and shear reinforcement diameter, we are going to use 10 mm. So first of all, you need to calculate the loading on beam B12 and sketch the shear force and bending moment diagrams acting on the beam by indicating the important values. And then secondly, you need to design the main reinforcement required for the beam, including all the checkings. So it's a full design of beam in this particular example. So this jetty here, it has a series of continuous beam which is 4 meter each, and then it has got a simply soldered beam that is at 0.25 meters in the transverse direction. And then the beam that we are going to design is on grid line B12, which is this particular beam with a cross section of 250 by 600 mm. And then from the cross section XX view, we can see that the thickness of the slab is 175 mm. So we are going to calculate the loading on this beam here, which is beam B12 based on the concrete thickness of 175 mm and also the beam of 250 by 600 mm. So the first step in the calculation is to determine the exposure class. So for exposure class for coastal structures, okay, we have corrosion induced by chlorides from seawater, okay, because the resort is on the coast. So we have seaside structures that we are going to build. And then for jetty, it is in the tidal zone where you have splash and spray of the seawater. Okay, so meaning that the exposure class of our jetty is XS3. So we have exposure class XS3. So from table E1N or table F1 as indicated in your design guidebook, so for exposure class XS3, the indicative strength class is C35/45. Okay, so this is the minimum concrete strength class that you can use for the design. And in the design, we have already specified concrete grade of C35. So we are using the minimum strength class. So the indicative strength class for exposure class XS3, the indicative strength class is C35/45. So we have structure class S4 with the minimum strength that we can use for our concrete. And then we go to table 4.3N under exposure class XS3. So for design working life or 100 years, for jetty we do not design for 100 years. It's just a normal structure, so we design for only 50 years. So there is no design working life of 100 years, so our structural class remain as S4. And then for concrete strength class, we are not using strength class more than C45/55. So this has been considered and there is no reduction, so still we have structural class S4. And then for member with slab geometry, no, we are designing a beam, so structural class does not change as well. And special quality control of the concrete production ensured, so it's not mentioned. So therefore, structural class still remain as S4. So there is no increase or decrease in structural class. Therefore, the structural class remain as S4. And then we assume that we are using bundle of bars with 3 numbers of bars in a bundle for 25 mm bars. So from table 4.2, for bundled bars, okay, we use the equation of equivalent diameter. So we have a diameter of 25 with the number of bars in bundle as 3 bars in the bundle. So we have 25 times square root of 3. Therefore, the equivalent diameter is 43 mm. So C min B is 43 mm. And then from table 4.4n, for exposure class XS3 and also structure class S4, we have C min DUR of 45 mm. So C min DUR is 45 mm. So comparing C min B and C min DUR, C min is 45 mm based on C min B and C min DUR. And then from clause 4.4.1.3 in bracket 1p, delta C deviation is 10 mm because we did not specify any quality control on the construction process. So in order to satisfy both bond and exposure requirements, we have C nominal as C min plus delta C deviation. So we have 55 mm. And then for fire resistance, we refer to Eurocode 2 Part 1-2 Table 5.5. So the beam that we are going to design has a width of 250 mm. For fire resistance of 1 hour, which is R60, and for beam cross dimension of 250, that is more than 200. So we can use this set of values, okay, where the axis distance A is 30 mm. And then if we refer to this note here, ASD is the distance to the side of beam for the corner bars or tendon or wire of beams with only one layer of reinforcement. So we assume 3 layers. In fact, if we consider 3 layers, we do not have to look at this sentence, but we still refer to it. And then in this example, just for your practice, so for values of B min greater than that given in column 4, no increase of ASD is required. So now this is column 4, and the specified B minimum is 200 mm, and we have a 250 mm beam. Therefore, we do not need to consider the increase of 10 mm in ASD for the corner bar axis distance. Okay, so even with the bundled bars, we do not have to consider increment of the corner bar axis distance already. So B minimum is greater than 200 mm, no increase in the axis distance for corner bars in single layer or for multiple layers. Okay, so axis distance from the table is 30 mm. So C norm plus the link diameter plus half diameter of the bar should be greater than 30 mm. So from there, C nominal is 7.5 mm or greater. So assuming triple layers of tension reinforcement and single layer of compression reinforcement, so in this case we have a beam like this. So we assume 3 layers of reinforcement. So the effective depth should be calculated to the center of this group of bars. So the calculation of effective depth for this beam here has to be to the centroid of this group of bars. Okay, so we have H of 600 minus of C nominal minus of link diameter minus of one diameter of bar minus of another half diameter of the main bar. So we have 498 mm. And then for the top bars, okay, so we assume one layer for the compression bar. So in this case, the effective depth D prime is just the nominal cover plus the link diameter plus half diameter of the main bar. So we have 78 mm. Next, we calculate for the design action. So for design action, we have permanent action and variable action. So permanent action, we have the beam self-weight. So the beam size is 250 mm by 600 mm. So we have 0.25 times 0.6 in meters multiplied by the density of reinforced concrete, which is 25 kilonewton per cubic meter. So we get 3.75 kilonewton per meter length. And then for the slab self-weight, okay, we use the thickness of the slab multiplied by the concrete density to get the load per unit area. Okay, so we get 4.375 kilonewton per square meter. And then we have slab finishing of 1 kilonewton per square meter. So the total slab permanent action is 5.375 kilonewton per square meter. So this 5.375 kilonewton per square meter is area load, which is the action on plan. Okay, so for this area load, we need to convert it to load per meter length on the beam. So we know that the slab loading will be divided into this load distribution because these slabs are one-way slabs. Okay, one-way slab meaning that you have the longer dimension over smaller dimension of more than 2. Okay, meaning that you have Ly over Lx greater than 2. Then it will be a one-way slab. So meaning that the load transfer will be one-way like this. Okay, so for one-way slab, the total area of load that is going to be transferred to this beam here will be this area. Okay, so this area of load will be transferred to beam B12. So the width of the area here is 4 meter, where 2 meter is on the left hand side and another 2 meter is on the right hand side of the beam. So we have already identified the area. Okay, so the total load is actually the force per unit area times the total area. Okay, but we are not interested in the total load. We're interested in load per meter length on beam. Okay, so to get load per meter length on beam, you just use the area load multiplied by the width of the area, which is 4 meter. Okay, we don't multiply it again by 8.25 meters because we want to get the load per meter length on the beam. Okay, if you get the total load by multiplying the area load to the area, okay, and then you divide by the beam length again, so it's still the same. Okay, you get the same load per meter length of the beam, but you are doing extra steps. Okay, so by using the area load multiplied by the width of the area, you get the load per meter length on the beam. So the total slab permanent action transferred on beam as uniformly distributed action is the area load 5.375 kilonewton per square meter multiplied by the width of the area of the slab that is going to transfer the loads or the actions on the beam. So we get 21.5 kilonewton per meter length. So that gives us a total permanent action of 3.75 plus 21.5. So that gives us total permanent action of 3.5 kilonewton per meter length from the beam self-weight, and then plus the permanent action on the slab that is transferred to the beam as uniformly distributed load as of 21.5 kilonewton per meter length. So we get total permanent action as 25.25 kilonewton per meter length. For variable action, the total slab variable action given in the problem is 4 kilonewton per square meter. So to convert this force per unit area, it's the same way of how we calculate the permanent action. So we just use the width of the slab that is transferring the action onto the beam. So the width of the area is the same, 4 meter, and then 4 meter multiplied by 4 kilonewton per square meter, we have 16 kilonewton per meter length. That is going to be transferred as uniformly distributed action on the beam. So for design action, it is equal to partial safety factor multiplied by the permanent action plus the partial safety factor for variable action multiplied by the variable action of 16 kilonewton per meter length. So we get 58.1 kilonewton per meter length on the beam. Next, we calculate the reactions with the design action on the beam, and then we draw the shear force and bending moment diagrams. So the maximum shear force is 239.7 kilonewton from the analysis, and the maximum moment at the midspan of the beam is 494.3 kilonewton meter. So based on the maximum moment, we design the main reinforcement as in accordance with Eurocode 2 section 6.1. So first we calculate the K value, and we get 0.228, which is greater than K balance of 0.167. So this means we need compression reinforcement in the design. So if we need compression reinforcement, meaning that our moment arm is 0.82D. So the moment arm is 408 mm. And then when we have compression reinforcement, we are actually designing the beam with X equals to the maximum allowable value, which is 0.45D. So that gives 224 mm. And then we check whether the compression reinforcement is yielding by checking D prime over X value. So we have 0.35, which is less than 0.38, meaning that compression reinforcement is yielding. Then we can use the design equations by taking compression reinforcement yielding at the stress of 0.87 FYK. So from the design equation, we get AS prime required of 725 square millimeter, and we get the required steel area for tension reinforcement as 2767 square millimeter. For the minimum reinforcement, we refer to Eurocode 2 section 9.2.1.1, where AS min is equals to 0.26 FCTM over FYK BTD, and it should not be less than 0.0013 BTD. So from table 3.1 of Eurocode 2, for FCK of 35 megapascal, the concrete tensile strength is 3.2 megapascal. So AS min is equals to 2007 mm square. So that is more than 0.0013 BD, which is 162 square mm, so it's okay. And then for maximum reinforcement, it is 4% of the cross section, so 6000 square millimeter is the maximum tension reinforcement. And for compression reinforcement also, the maximum reinforcement area is also 6000 square millimeter. So based on this information, then we can start to provide the steel. Yeah? For tension reinforcement, we use 6H25, which gives us the total area of 2946 square millimeter. And then for the compression steel, we use 2H25 to give the area of 982 square millimeter. So for the tension steel, we use 6H25 with AS provided of 2946 square millimeter, provided in 2 layers. So just now we assume 3 layers with smaller effective depth D. So therefore the design is on the conservative side, so it is okay. So what it means here, now the actual design we have only 2 layers of steel. So with 2 layers of steel, the effective depth is actually deeper than what we have assumed earlier. So with deeper D, you are going to get less AS required. So because of that, we can continue on the design. And then for the compression reinforcement, as mentioned just now, we use 2H25, so provided steel is 982 square millimeter. So AS prime provided is 982 square millimeter. So now we can calculate the new effective depth based on the arrangement of steel that we have. So the new effective depth, or the one that reflects the actual design situation, is 510 mm. And then for shear reinforcement, the design shear force at both ends of the beams, the maximum shear force is 239.7 kilonewton. So we use this as the maximum design shear force for the beam design. So shear reinforcement design is in accordance with 6.2.3 of Eurocode 2. So first we calculate the concrete strut capacity at angle theta of 22 degree and at angle of 45 degree as well. So for angle theta of 22 degree, we get VRD max of 476.4 kilonewton. And for theta equals to 45 degree, we get VRD max of 690.8 kilonewton. So from the design shear force of 229.7 kilonewton, it is less than the VRD max at theta of 22 degrees. So we know that the angle will be less than 22 degree in this particular beam. So we use the minimum angle of theta equals to 22 degree in our design. So using the design equation, ASW over S is equals to V ED over 0.7 at FYK D cotangent theta with theta equals to 22 degree, we get ASW over S of 0.482. So for 10 mm links, ASW is equals to the area of two 10 mm bars, so it's 157 square millimeter. Substituting ASW equals to 157 square millimeter, we have spacing of link is equals to 326 millimeter. And then referring to Eurocode 2 clause 9.2.2 in bracket 6, the minimum link spacing S max is equals to 0.75 D, so that is 383 mm. And then referring to Eurocode 2 clause 9.2.2 in bracket 5, minimum links specified is ASW over S is equals to 0.08 BW square root of FCK over FYK, and we get 0.237. Substituting ASW equals to 157 square millimeter, we get spacing of 662 millimeter. So based on the three spacing that is calculated, maximum spacing is governed by the one calculated from the design calculation, which is 326 mm. So we can use 326 mm as our reference, and we provide H10 at spacing of 300. Why don't we use 325? As I mentioned, we use multiple of 25. Because in design, normally we specify maximum spacing of 300 mm for all the reinforcement. Okay, so in practice, normally we do not specify spacing of reinforcement more than 300 mm. Okay, so for spacing of reinforcement, we usually do not provide spacing more than 300 mm, so this is considered as the minimum links. Okay, so the design reinforcement for shear will be H10 at spacing of 300 mm. Strictly speaking, we still need to design the additional tension reinforcement for shear, okay, but I'll leave the calculation until the end of this tutorial to show you how we provide the reinforcement based on this calculation. So bear that in mind, that we still have additional tension reinforcement calculation for shear. Next, we check for deflection at serviceability limit state in accordance with section 7.4 of Eurocode 2. So to calculate for deflection, we need the information of the reinforcement ratio rho, which is as required over BD, given as 0.0217 from the calculation. And then we need the term rho 0, which is square root of FCK multiplied by 10 to the power of minus 3. So that is 0.0059. And then we also need the term rho prime, which is the compression steel ratio. So it is 0.0057. And then from table 7.4n, we have a simply supported beam, so the value of K is 1. And then the value of rho is greater than rho 0, then we use equation 7.16.b from Eurocode 2. So from equation 7.16.b of Eurocode 2, we get L over D basic, which is 14.8. And then modification factor for beam span greater than 7 meter, we have 7 over 8.25 meters of the span of the beam, so we have 0.85. And we get another modification factor for steel area provided. So the provided steel area is 2,946 square millimeter divided by the required steel area of 2,767 square millimeter, we get 1.06. So multiplying L over D basic to these factors, we get 13.3 as the allowable L over D ratio. And then from the structure, we get L over D, which is the actual value of 8.25 meters over 510 mm. So we have 16.2, which is not less than the allowable L over D ratio. So the deflection check is not okay in this situation. So what should we do? So normally if the L over D ratio does not satisfy the allowable L over D ratio, we look at the difference. So the difference here is still quite near, is 16.2 and 13.3. So If we look at the modification factor for steel area provided, it's only 1.06 from the calculation, so we can still increase the factor for modification for steel area by increasing the steel area provided. Okay, but this factor cannot be more than 1.5, so take note of that. So now we can change tension reinforcement to 8H25. So for 8H25, as provided is 3928 square millimeter. So with this provided steel of 8H25, the modification factor for steel area provided becomes 1.4 and is less than 1.5, so it's okay. So with this new modification factor for tension reinforcement provided over tension reinforcement required, we have L over D allowable of 17.6. So 17.6 is greater than 16.2, which is the actual L over D ratio. So deflection check becomes okay after we have added 2 more steel bars as tension reinforcement. So after deflection check, the new arrangement of reinforcement is shown in this figure here, okay, where we have HH25 for the tension reinforcement and the compression reinforcement still remain as 2H25. Next, we need to check for cracking. So from table 7.1N with exposure class XS3, and for reinforced concrete members, we have maximum crack width Wmax of 0.3 mm. And then for steel stress, we are using the quasi-permanent load of GK plus 0.3 QK. Okay, so that gives us the steel stress at serviceability limit state as 225 megapascal. And then from table 7.3N, for steel stress of 225 megapascal, it is slightly less than 240 megapascal. So we use 240 megapascal as our reference, and that gives us 200 mm spacing for maximum crack width of 0.3 mm. So we have maximum bar spacing for crack control is 200 mm. Next, we calculate the spacing for the arrangement of steel that we have designed. So we get 24 mm, so it's less than 200 mm, so it's okay. Next, we look at clear spacing. So for clear spacing, from our calculation, it is only 7 mm. So 7 mm definitely cannot satisfy the maximum distance between bars of 30 mm as we have calculated from these three requirements from section 8.2 of Eurocode 2, by assuming that the largest aggregate size we use is 25 mm. That gives us H aggregate plus 5 mm of 30 mm, which is the minimum clear spacing. Therefore, we need to arrange the reinforcement again by just assuming bundle bars of 4, okay, in the design. So in the bundle bars of 4 bars in one bundle, our effective depth has been reduced to 485 mm. So this is less than the 498 mm that we use in our bending design, and also 510 mm that we use in shear reinforcement design. So strictly speaking, you have to repeat the design calculations based on this new effective depth D of 485 mm for both bending and shear. So you can do the checking by yourself, okay, by doing the calculation again for bending and shear reinforcement design using this new effective depth of 485 mm. Okay, but I reckon that it is okay. okay, because it's not much difference, right? But as your own exercise, please go through the calculation again using this effective depth of 485 mm. So if you arrange our steel bars this way, then the clear spacing becomes 70 mm. So it's greater than the limit of 30 mm as we have calculated before. And then for detailing, we have the detailing as shown here, where we provide a layer of 4H25 and then another type of reinforcement which is 4H25 to give us 8H25, so that we can curtail half of the numbers of bars near the support of the beam, okay, at 0.08 L from the side of the support. Okay, so 0.08 L is 660 mm, so we round it to 650 mm. Okay, so this number has to be less than the 0.08 L, so that you have a longer bars provided, okay, towards the end of the support. And then for the compression reinforcement, we have 2H25. Okay, so it's provided from the support to support. And for the shear reinforcement, we have H10 at spacing of 300 from support to support as well. And then if you cut across section 1-1, you see 8 bars as tension reinforcement. And as you cut across section 2-2 near the supports, okay, then you see only 4 bars. We have already cut off 50% of the bars. Okay, so we only need 50% of bars near the support. Okay, as you can see from the additional tension reinforcement for shear calculation later. So for the additional longitudinal reinforcement calculation is in accordance with Eurocode 2, section 6.2.3 in bracket 7. Okay, so the additional tensile force is 0.5 VED cotangent theta. So cotangent theta is 25 degree, yeah? Okay, where we use the minimum angle. So we get 299.7 kilonewton. So the additional tension reinforcement required is the additional tensile force divided by the design strength of the steel, which gives us 689 square millimeter. And then we need 25% of S required for bending near the end of the supports. Okay, so 25% of 2767 square millimeter is 692 square millimeter. So as you can see, as I mentioned before, providing 50% of the S required near the end of the support for simply supported beam is sufficient to satisfy both bending and additional tension force from shear. Okay, so the required steel area is 1371 square millimeter for both shear and bending. Okay, so the provided is 4H25, which gives us provided steel area of 1964 square millimeter. So it's okay. Okay, so that's all for the explanation on the solution of question 6 of tutorial 2. Thank you very much for listening and watching.